In the last few classes, we went through stresses and we saw there are two kinds of stress. One is shear stress, another one is normal stress. And we understood in great details, the shear stresses and normal stresses, where they appear and how they appear. And also we have looked into the transformation of the stresses, right? So uh, when you look at a material and you look at the loading on the material and its boundary conditions, you feel that it might be only an axial stress. For example, a chalk with an axial load or a bar with an axial load. We feel that the member will have an axial load only. But we saw with our analysis that if you change your lookout, in the sense you change your look of the plane or orientation of the plane where you are looking at, things change, right? Things change from normal to normal and shear. And there can be planes where there is no shear, and there can be planes where there is no normal, right? We have seen all these kinds of examples through our analysis, and this is a nice way of looking at materials that uh, no matter what kind of loading, yes, definitely it depends on the direction of the loading, it depends on the magnitude of the loading, but the material point will get shear and normal both at different angles of orientation. Okay. And then it becomes very important for us that what is the effect of the shear and normal stresses on the material? Because when you see a normal material under loading, for example, the building that you are sitting on, or the tree that you are seeing from the window, probably, or the pen pencil that you are having, when you put some load, can you see stress? You cannot, right? We don't see the stress developing in the material. Okay. Next class, you let me know. I'll show you some videos where you can probably visualize stress. Okay, but on a general material, it is not easy to visualize, or it's not possible to visualize stresses. Right, but we see, right? We see you take a rubber in your hand and pull it. You see that the rubber elongates, right? Okay, but as an engineer right now, I have not changed the slides yet. I'm just discussing right now, Satvik. Swatik, sorry, not Satvik, Swatik. So you take a rubber in your hand, and then pull it. Obviously, as an engineer, when you are pulled, you have given an axial load. And since there is an axial load, there should be some stresses developed within the material. But what you see is a change in the length of the material. Okay? So the manifestation comes as a change of length or change of geometry, right? Instead of length, I can say length and breadth. So change of geometry, right? So, or change in orientation. Anything can happen because of underloading. Now, in engineering mechanics, you have learned all those things, but you did not pay attention to, or it was not part of your syllabus. That's why you did not pay attention to the changes between point and point within the material, 2 points within the material, right? We have always understood in engineering mechanics that the material or the body is rigid and there is no relative motion between 2 points, two separate points within the body. In this course, we have to first understand there can be relative motion between the points, 2 points within a body, and this relative motion. Yeah, Kanikeswar, I'm speaking. I hope everybody can hear me. And these 2 points are the deformation or the relative motion between these 2 points can be calculated, and that's what is also one of the measure in solid mechanics that we need to be learning. Okay, and that's called strain. So today our objective is to understand what is a normal strain and what is a shear strain. Tomorrow what we'll do, we will extend these studies or under our understanding to development of how to calculate strains, right? Normal and shear strains on a material point, right? And the next class we will solve a few problems, and with that strains will be. No, Kanikeswar, I'm still in the first slide, so you have not missed anything. Okay, chalo, let's go ahead. So concepts of strain. So as I was discussing, so this part of the lectures are taken from these two books or notes, and if you want, you can take it and read them directly instead of having a filter from me. Okay, so what do we mean by strain? So as I was discussing, when we give an applied force to a structure, there are some internal forces that are developed, right? And those internal forces are used to calculate stresses, right? And we know there are two kinds of stress. One is normal stress, one is shear stress. Normal stress is given by sigma ij, and shear stress is given by tau ij, right? We learned all those things in our last classes. Now, as I said, we cannot visualize stresses, right? What we can visualize is the deformation within the body, change in shape and size of the body, right? This is what we can visualize. Therefore, we need to have a measure of this for the, and then we have to relate that measure with forces. This is our actual job, right? To relate the deformations that we're seeing in a body with the forces that I have given to the body, right? These are the two things I have to relate, because both are my observation. So if I take a beam, let's say, so we have taken a lot of axial members as examples. Let's take a beam, for example, today for a change. If I have a beam and I give a load, what are we going to observe? Very simple, right? You have seen it already. You can do it, at your home also. Take up metallic scale and put it between two chairs or between two tables, hold them tightly, or put some books on this support. So put some books here to support it like this, and then you put a load, put your load by your hand, and you will see that it will start deforming like this, right? The central point will start deforming like this. Now that deformation you can visualize, right? This is what you can visualize. Okay, it is visible. Now you will probably be interested in understanding how much load will lead to this kind of deformation of delta. Okay, if I increase P to double, will delta be double or not? Or maybe lesser, I don't know. If I give another force somewhere, how will delta change? Okay, all those things can come in your mind, right? So you would like to relate these two, because these are the two things that you can visualize. Whatever is happening inside, it's part of understanding and analysis. But when you measure these two, and you have to relate them. So one way of relating them is to relate it with stress. We know now that one of the internal mechanism, that is the development of stress, is what we know how to find. Not for beams, but for axial members, we know how to find. Right? And then we know also how to calculate displacement. Now, how to relate them? We relate them using strains. Okay. So today we are going to learn about strains. Before we learn about strains, we need to learn about deformations or displacements. Okay. Once we learn what are the deformation and displacement possible in a material body, in a material frame, then we will move to how to calculate strains. So probably calculation of strains will be part of the next class. Today's class, we will just learn the definitions and understand, if I have been given a material body or a member, how can I find strains in it? Okay. So before we go to strains, let us discuss about displacement and deformation. When you have body, you give some load to the body. When you give that load to the body will show that load by some deformation or displacements, right? We have already discussed that. Now there are two kinds, as an engineer, we divide it into two parts. One is rigid body motion, the other one is deformation. When I say rigid body motion, you all know, you have done it in one semester in last year. The body as a whole moves without changing its shape, right? That means there is no relative motion between 2 points within the body. Okay? Whereas in deformation, the body's relative motion between the points of the body will be active. So body will start moving. Take a eraser in your hand. Okay, try to rotate it. If you rotate the eraser, you will see there are different points that are rotating about each other, and they are not uniform all through. Okay, therefore there is a relative motion between them. So when you take a rod and rotate, right, not twist, you rotate it, you see that rigid body motion happens, right? Everything rotates with the same thing. So let's say you take a rod, okay? So that will look, the cross section will look like this. Now, when you rotate it, what are you going to observe? You're going to observe the same cross section, right? If I don't color it. So you are not going to see any relative motion between any two points in the rod. Right? But if I have a very flexible rod, let's say, I don't know, maybe your headphone wear or your computer wear, something you take, and that is flexible enough. Let's say, the diagram is not correct. Let's say that is flexible enough. What will happen if I take a cross section here? And you give a load, and the boundary is not free, okay? So there is another load that is acting here, like this. What you will see, two different points will deform differently, right? So if I have a straight line here before deforming, the straight line may deform like this after deformation. So that is what change in relative motion of relative two points, the relative motion between 2 points, and that's called deformation. We'll be making it more clear. Okay, so this is what is defined here. You can go through the writing here. In addition to translation, a body can rotate also. Rotational example I was giving. On rigid body, the lines that rotates are of equal amount. And for an angle, if the angle between the two lines in a rigid on a body, then they are deformed, right? For example, if you have a perpendicular line, okay, when you have a rigid motion, they will remain perpendicular like this. But when you have a deformation, then they may move like that. Okay, so if a perpendicular line remains perpendicular before and after deformation, then it's a rigid body motion. If they don't, then it's not a rigid body motion. There is some deformation that is going on in the material, elastic deformation. We call it elastic deformation. And let me write it also, elastic deformation. For us, elastic deformation. There can be plastic deformations also. If you take a plastic, you can see that there is a plastic deformation. We'll talk about this probably when the material properties come into action. Okay, so here is an example. So this is how we test materials. So this is a UTM body. UTM is universal testing machine. So what it does, it pulls a material. This is according to ASTM standard. You are supposed to do these experiments in your second year. I don't know what's happening to that. And you clamp them, the top and the bottom, and then what you do, you mark some lines, okay, and then you pull with some load, and you will pull till it fails, okay, to see its yield values. We'll talk about this a little later, maybe in another 1 week's time. So if you pull, what are going to happen? So if you have marked these lines, if you see that those lines will elongate, right? This line has elongated, this line has rotated a little bit, sorry, and this line has squeezed. So when you give a pull on the material body, the body's geometry has changed. It has extended in length, it has squeezed on this side, and this line is rotated a little bit. This is its deformation. Now, this measure of this formation of a flexible body under loading is called strain. Okay, so as I said in the last time when we did stresses, that we need to, we give a lot of loads to a lot of bodies, and the bodies will have different geometry, right? But we need to standardize somewhere that to measure and to compare for failure. So we need to find some normalization somewhere, and that is how we do is we divide load per unit area and find what is its stress, right? And we said that a material should not go beyond a certain kind of stress that are given to the, or ultimate stress that is given to the material. Similarly, for strain measure also, we do some kind of normalization there, that if I have the same kind of, geometry of a structure or same material made up of, and then I just extend the length of this. So what will happen? The length will change, right? When you pull it, the longer length will have a longer pull and the shorter length will have a shorter pull, right? So change in deformation is different. But we want to somewhere normalize this. So what we do is we calculate strain. Okay, the strains can be because of mechanical stresses or because of thermal changes in the material. All those things are only part of understanding. Right, the relationship between stress and strain is called constitutive relationship, and this is what we are going to learn from the next week, I think. That involves, not next week, next to next week. And it involves material properties. So while calculating stress, we did not bring in material, right? We wrote it as P by A. While calculating strain also, we will not bring in material property, we'll write it as delta by L. So there has to be material properties somewhere bringing in. So that will bring in the relationship between stress and strain. Remember this, don't forget it. Okay. Now, how does this deformation happen? So I will just go through this a little bit in detail. So pay attention. Let's say that I have a material body like this. This was before giving any load onto the material, and its coordinate system was x and y like this. I have chosen a point P and a line across the point. Okay, the coordinate of this point is xyz or xyz. Okay, after deformation, after giving the loading, so this was his original configuration. After giving loading to the material has changed its shape. You can see the change in geometry happened. Okay, so it was a bigger shape. It has now come down to a smaller shape, and there is an orientation. So the angles have changed between them. So there is a little bit of kind of distortion in them. And the point that was looking at is now a point called P dash, because it's a different, it's the same point on the material frame, but the point may displace itself from its original location. So we have to name it as P dash. And the straight line that I had is no more a straight line. It has just become a curved line because there is a relative motion between the points. So this is not a rigid body motion. This is a elastic deformation. Okay. Now my objective will be to understand how much deformation has happened in P and how to calculate that, right? That would be my objective. Similarly, if you have a line here, as I have given here, a line L0 is the length of the line in original configuration. And when you move to a deformed configuration, we see that line L0 had moved to L0 plus delta, right? The length has changed as well as the orientation angle has changed. All right. So it was initially between points P and P dash. Now it is between points P dash and P bar dash, right? Its original configuration, and P dash bar as a deformed configuration, right? So there can be two things. As you can see, there are two things in this material point that has deformed. One is it has changed in length. The other one is it has changed in its orientation. Okay, in the deformed configuration. So these are called deformation. The change in length is called normal strain or deformation due to normal stress, and change in shear or the rotation is called shear stress, the shear strain, which is mostly because of shear strain. And we know that even a normal strain can give rise to shear strain at some other orientation, and therefore there will be shear strain developing in some other orientation, even if you give only axial stress to the body, stress to the body. Okay, so basically there are two distinct strains that can develop in a body. One is which helps it to elongate, change in length. The other one is which helps it to rotate. Okay, so these two are primarily two strains that we get, and these are the two that we have to calculate as we go ahead. Understanding of deformations, and we have also given some basic things like there can be rotation and there can be elongation. These are the two kind of things that we get in deformation, right? So these are all elastic rotations and elastic elongations. I'm not talking about rigid bodies here right now. Okay. So those two things give rise to something called normal strain and shear strain. we will now understand what are normal strain and what are shear strain. So please, I will give 5 minutes at the end of this class where you can ask me as many questions as possible. This is very important part for understanding. So please pay attention. Normal strain. So as you can understand from the name itself, normal strain is elongation. Okay. So if I have a bar member, we take always example of bar member because it's a very simple and easy to understand. And then we complicate our understanding as we go ahead in the course. So this is a bar member, and I have given a load here, let's say, okay, P load. Let's say a P load. If I give a P load on the bar member, what will happen? The member will elongate. Tensile force has been given. So it will have a tensile stress on its material, right? So the material points will start moving. So the strain has become now this. So body has moved from L0, what is undeformed length or original length we call. That means before the application of load P, the length was L0. And as we have applied load P is still there. As we have applied the load P, the material has elongated. Let's say it's an elastic body, a rubber band or something, which has elongated, and the elongated length is this much. So now the deformed length, we call it deformed length, is L0 plus delta, which is L. Now, how do you calculate strain? There are two ways of calculating strain in mechanics. There are many others. So these two are very famous in mechanical engineering. One is called Lagrangian measure. The other one is called Eulerian measure. Eulerian measure you might have heard in fluid mechanics a lot. In solid mechanics, we mostly deal with Lagrangian strains, most of the time, unless very specific problems may need Eulerian description. Now, what we call as average strain is L minus L0. That means change in length. This is change in length, right? So this is change in length. Divide by some reference length, L ref. So this is reference length, okay? The change in length is fine, right? We know my initial length, I know my final length, so I can make change in length. Now, how do I choose reference length? So there are two ways of choosing reference length. One is you can choose the initial length to be its reference length. L is ref is L0 itself. Okay, so we call that Lagrangian strain. And when we choose reference length as the final length, we call it as the Eulerian strain. Okay. So the first one, the Lagrangian strain, is based on original configuration of the material. The second one, which is called Eulerian strain, is based on deformed configuration of the body. Okay. So the coordinate system have changed. So initially the coordinate system was its original length. If you see here, original length, and next the coordinate system is the deformed length. Why do we need deformed length? Because in many things, many problems, we know the final state. We don't know the initial state. Okay. Many problems, especially in fluid mechanics, it happens. Even if I have to understand how much strain the earth has gone through, I have no idea how it started, right? I have all the ideas at the present state. So I know the present configuration, the deformed configuration. I don't know, I don't have any idea about its previous or maybe 1,000 years before this configuration or a million years before this configuration. Okay. So in those cases, having a Lagrangian strain is a misnomer in the sense small strain or small deformation, both of these Eulerian and Lagrangian strain will give rise to same results. Okay. So till the first order sense or the first term in a Taylor expansion, if we go, both these strains are same. Only for large deformation, the large strains, they differ from their solutions. Right? So we don't have to bother about that because we are not doing large strain in this course. We are doing very small strains and very small deformations and rotations in this course. So for us, it is always L ref is L0. Okay. For us, L ref is equal to L0. This is very important. We don't change here because we are only looking for very small deformations, not large deformations, or small strains, not large strains. Okay. So pay attention here. So for us, L0 is always the undeformed configuration of the body. So how do you calculate normal strain? Normal strain is now given by delta by L0. All right. Okay, this is what has been written here. If you have less than 1% strain, that is what going to happen. Okay. Now for a shear strain, how do you define a shear strain? Now, as I said that shear is a change in angle, right? So if you give a pure shear to a body, what will happen? Let's say I have a body here and I give a pure positive shear to the body. What is going to happen? The body is going to, this is the point. So it's going to move like this. So it is going to look like this, right? Because of the shear, it is going to distort a bit and it's going to move like this, right? So if you look at two lines that are perpendicular to each other here, like this, and the other line is like this, what will happen? You see that this body is trying to move like this, right? Because this corner is trying to move out because of these two forces. These two forces trying to pull the corner out like this, right? Whereas these forces are moving away, right? So this point will try to go inside. So the forces acting on this side is on this direction. So if you draw the Morse circle, you will see if you have an element on this direction, so 45-degree angle element, you will see that this one is acting and there is compressive force that is acting here. Do that and see. So therefore this point will try to move inside, this point will also try to move inside, both of them, but this point is trying to go out and this point will try to go out, and therefore it will look like this. So this has moved in, therefore this radius, this diagonal will squeeze, whereas this diagonal will elongate. Okay, and it will make an angle here. So our initial angle here was 90-degree. Now the angle has moved from 90 to some other point. So this is that point, let's say. Right. So this was, let's say the bottom side is fixed. So if the bottom side you fix it and you give a shear force here, there is only one shear in that case is acting. There won't be any two shears. So if there is only one shear that is acting, it will go like this. So this was your initial configuration of the body. The deformed configuration will be something like this, right? Because of the shear, it will move a little bit. Put a rubber at your hand, elastic rubber or eraser, and try to give a shear force. You will see the same thing happening to the eraser. It will start making an angle. This angle is called the gamma shear strain of the material. How do you calculate it? The angle before deformation was pi by 2. The angle after deformation is this angle, which is 90-degree minus gamma, let's say. Then the shear strain is this angle, right? 90-degree minus its initial configuration minus its deformed configuration. That is what gives you gamma as your shear strain. Now shear strain name should have the plain name, because we all understand that shear strain, when you talk about shear stresses, it's become important that we have to write which plane it is acting and which direction the force is acting. Therefore shear strain should also have the same representation as the shear stress, gamma xy, right? Okay, is that shear strain understood? What we have here, yeah, that same picture that I drawn here is the same here. Okay, so this is how you calculate the shear strain. Now in this picture we had only one angle change. In this picture there will be two angles change, right? Since the material body, will assume, since the material body is symmetric, perfectly symmetric body with subtle symmetric loading, very small element, there is no discontinuity between them. We'll assume that both of them to be of same gamma by xy, gamma xy by 2 and gamma xy by 2. That's an assumption. It may not be true if the material is is not homogeneous or not uniform at that point location. Okay. So that's y2 and y2. Therefore, total deformation or total strain is half gamma xy, half gamma xy becomes only 1 gamma xy. So either we can draw this picture or we can draw this picture. Both of them are same representation of shear strain. Okay. Please pay attention to shear strain because it's a little bit difficult to grasp and understand, but I think you can do it. So again, another slide on shear strain here. All right. So when we say shear strain positive, if the shear stress is positive, shear strain is also positive, and that means the angle has moved from 90 to lesser than 90. Okay. If the angle has moved from lesser than 90 to greater than 90, it's a negative shear strain. So this is a positive shear strain here, where the angle has moved to a lesser than 90. This is a negative shear strain here because the angle at A was 90 and now it is more than 90, right? Obtuse angle. So it is a negative shear strain. And this is a positive shear strain. So if I have this body here, back to this one, if you see this point A and the angle was a 90 degree and reduced to lesser than 90. So this is a positive shear strain. But if you look at a point here, instead of looking at this point, I move to this point. This point was 90 before deformation, but now it is an obtuse angle greater than 90. So that's a negative shear. So I changed the point. Okay, this was the point, and now I changed to this point. The shear has changed from positive to negative. Okay, all right, is that understood? This is explained very well in these notes that I have written for you. Please go through this. Whatever I have discussed is the same thing. The angle has moved to a lesser than 90 value, so it's a positive. The angle has moved to a greater than 90 value, so it's a negative. So you can see the shear directions are also negative here. Okay, so if you have a negative shear direction, this diagonal is going to elongate and this diagonal is going to squeeze. So this has reduced in length and that has increased in length, right? And therefore this shear is a negative shear strain, whereas this one is a positive shear, right? So this diagonal is increasing and that diagonal is decreasing in length, and therefore this is the deformed configuration that it can have, and so it's a angle that is lesser than 90, so it's a positive shear strain. Okay, with that I'll stop today.